Good afternoon, everybody. Today we're taking a look at another challenge problem, perhaps one of two this week, since this one is relatively short. It involves the concept of static friction and a rope. In fact, it's probably one of the shortest problems I've ever seen because it's only one sentence long, as you can see here. If the coefficient of static friction between a table and a uniform mass of rope is mu sub s, we need to figure out what fraction of the rope can hang over the edge of the table without the rope sliding. And I know that it can be a rather confusing problem because we were only given one physical quantity, the coefficient of static friction, which tells us absolutely nothing about the length of the rope or the mass of the rope or anything in that regard that might be useful to figuring out the fraction that can hang over the edge. So naturally the question is, what are we supposed to do here? So I would recommend thinking of the entirety of this rope as being broken up into two parts, like this. And we have one part being the portion of the rope that's still sitting on the table here. And then the other part is the portion of the rope that's hanging off the edge. And the idea is that let's try and use free body diagrams to figure out all the forces on these two parts and do Newton's second law and see if we can't get an answer or a result or something that only includes the coefficient of static friction. That's the goal. So let's move on to the free body diagram of the portion of the rope that's still sitting on the table. The first force is going to be the weight of that part, and that will be the difference of these two quantities, right? So we're taking the weight of the entire rope minus the weight of the part that's hanging off. That tells us the weight of the part that's sitting on the table. And to oppose that force, there's going to be the normal force acting on the rope from the table. We know that the coil of the rope hangs over the table, and the part that's hanging over is trying to pull on the rest of the rope. And that force, that pull, is going to be represented by tension here. And since the overall motion of the rope is to try to pull the rest over the side of the table to the right, there's going to be the force of static friction acting in the opposite, force of static friction acting in the opposite direction here. And that is it for all the forces acting on the part of the rope that's still sitting on the table. Now what about the part of the rope that's hanging over? It has far fewer forces acting on it. There's just the weight of the part that's hanging over acting straight down. And there's no normal force because there's not a table for that portion that's hanging off to rest on. So instead, we have the tension of the rope pulling up. And this tension and that tension are going to be the same length, the same magnitude. Okay, they are the same. And that's it for all the forces on both of these parts. Next, let's move on to summing up the forces on the part of the rope that's sitting on the table. We know that we start with the sum of forces equals ma near the top, where m is the mass of the rope that's sitting on the table specifically. If we do the sum of forces in the x direction, we have the tension pointing in the positive direction and the static frictional force acting in the negative. So that's why it's written this way. The rope, the part of the rope that's still sitting on the table, it's not getting pulled off yet, right? It's still just sitting there. So the acceleration in the x direction is 0. And we can exchange this static frictional force for the expression that we're familiar with. It's not mu sub kn, but it's mu sub sn this time. And furthermore, we can take this quantity and move it to the other side. So now we have an expression for the tension in the rope. And one thing I would recommend is turning to the sum of forces in the y direction to get a definition of what the normal force is. And we'll do that here next. we see that the sum of forces has the normal force pointing in the positive direction, and then the difference of these two weights pointing in the opposite. So what I would like to do is move this quantity, this difference of weights, to the other side. And that will look like this. It seems like I have some extra text here. I'm going to kind of get rid of this. Just treat this as n. It's the same thing. So we have n equal to the difference in these weights. So that means I can take this expression, since that's what the normal force is equal to, and I can plug it in right over here. And that's what I'm going to do next. So we have the tension being equal to the coefficient of static friction multiplied by this difference in weight. And we can't go any further, so I'm going to make an underline under this expression, and we'll come back to it later. Next, we have to do the sum of forces on the portion of the rope that's hanging off. We have F equals ma at the top, where m is now specifically the mass of the rope, the part that's hanging off, right? It's no longer the part on the table. There's no motion in the left and right direction, the x direction, so just sum of forces is 0. Easy enough. In the other direction, sum of forces in y, we have the tension pointing in the positive direction, and then the weight of the portion of the rope that's hanging off pointing in the opposite. So that's why we have that set this way. And since the rope hasn't pulled the rest off the table, there's no acceleration. So the acceleration in the y direction is also 0. And we can take this weight portion and move it to the other side, which gives us another expression for the tension, which I'll underline here. So let's bring both of those expressions for the tension onto the same page, because the idea is that we want to set them equal to one another and get rid of it, because we don't know what the tension is. Nobody gave it to us. It wasn't in the problem description. So if we can set these two quantities equal to one another to get rid of the tension, that's what this looks like down below. And the first thing I would like to do is distribute this coefficient of static friction to both of these weight terms, which will look like this. And since we don't know anything about weight, let's exchange weight for mg, but we'll have to be careful about what m we're looking at. So if we enter that in next, we have the mass of the portion times g here, the mass of the rope times g here, and then the mass of the portion times g here. So it all kind of corresponds. What's nice is that we have g in each term on both sides, which we can just eliminate. We don't need that anymore. And we're left with this. Now, we don't know what any of these masses are, so we need to find a way to algebraically manipulate this result to just give us the coefficient of static friction in some way, shape, or form. So let's take this equation down here on the bottom and bring it to a fresh page, because I'm kind of running out of room here. And notice I brought the mass of the portion of the rope terms on both sides, which allows me to factor out the mass of the portion on the left-hand side. So I'll have 1 plus the coefficient of static friction in parentheses here. And here's where the trick comes in. I'm going to divide both sides by the mass of the rope, m rope here, and then m rope here. So that'll get rid of that. And then I'll divide both sides by 1 plus mu sub s. 1 plus mu sub s. So it's a little messy here, but you'll see how this comes together on the next line. Because now, if I rewrite this cleanly using this text, I have a fraction of masses equal to a fraction involving coefficient of static friction. And surprise, surprise, that is exactly what we wanted. We don't know anything about the mass of the portion of the rope or the mass of the entire rope but we don't care. We don't need to know that. We can get that information from the coefficient of static friction alone. That alone will tell us all of this. So this is a fun problem because it gives you a unique perspective into being able to solve a problem using something you totally don't expect. Maybe you're an engineer or something and you need to find out this ratio, but you're not able to measure it. Well, you've got an extra tool in your back pocket that allows you to do the exact same thing, but maybe in a way that you can measure. So, very interesting problem. Very cool to see alternate methods to figuring out the quantities that we want. That's it. Thanks for watching.